and and now we're going to discuss about the Muller's method. It's the same as how you do it. Now, basically, we start with the recurrence relation. The recurrence relation is given as what I've written as k plus 1. It's basically equal to this one, and also along with that, we will have to consider these following a0, a1, a2, and d. Now, basically, we will be using this in order to find out the rate of convergence of the Muller's method. After that, we have to extend it to by using the Newton-Raphson's method in order to find out the rate of convergence. So you just remember these constants a0, a1, a2, and d. Xk equals to r plus xk. It is the actual form of xk, and f of r plus xk is also expanded in the form of Taylor series expansion. The same goes with f of xk minus 1, xk minus 2, which I've denoted in equation 2 and 3. That's what it is. And I've written equation 4, 5, 6 for xk minus 1, xk minus 2. Now these things are actually found out because they needed to be substituted in the equation which I've just showed you before. Then you find out fk minus 1. It's of a simple procedure, you can follow it up. Just simplify it from there, and then you reach equation 7. Similarly, the same thing goes for fk minus 2. It doesn't need to be done again from the beginning. You just have to replace k minus 1 with k minus 2, hence obtaining equation 7 and 8. Now I have showed you the values a0, a1, a2, and d as before. In that particular a0, we are substituting the values in this equation. Right now we have substituted, and then we are proceeding by further simplifying this. Epsilon k minus 2 is taken common outside, and which gives you this equation. Is d is actually equal to that term in the denominator, so that gets cancelled out, thus leaving you with this following value of a0. Then you further proceed. By doing so, you get a0 to be f double dash of r by 2 factorial. That's it. So you found out the value of a0. Now we need to find out the value of a1. That is the next. Now a1 is written as this particular thing. Actually, I've just substituted the remaining values in this and giving you this term. Proceed in the same way by taking epsilon k minus 2 into epsilon k minus 1 and substitute the value of d. Both the value gets cancelled. That's what you get. And when you further proceed, you get the equation to be of this form. Again, you just simplify the equation. By doing so, you'll be able to obtain a1 as such. You keep proceeding in further on like this. Some terms inside the bracket gets cancelled. I've shown it that you have even marked which terms actually gets cancelled, and you'll be reaching this particular term. Now in this term, you just multiply 1 by epsilon k minus 1 minus epsilon k minus 2 inside, and while you do that, the terms in the numerator and denominator get cancelled, and thus giving you the value of a1. So now we have obtained the value of a0 and a1. Note that epsilon k cube can be neglected. It's not needed to include that because it's a negligible amount, so need not include that. Also, we're finding out the value of a2. We have obtained the value of a2. I want you to know that the f of r is actually a root which equals to 0. So a2 becomes of that form. Now we are going to substitute the value of a0, a1 and a2 in this following equation. Just put what values of a0, a1, a2 that you have found in this, and while you do that, you just cancel out the terms and you have obtained the value of a1 square minus 4 a0 into a2, which equals to f dash of r whole square. That is the actual value of it. Now you put this particular value in a1 square minus 4a0 into a2. When you do that, you get the value on the RHS as shown. Now the square only goes off because of the root. Just further simplify as such by taking 2 into f dash of r outside and leaving you with this term. Now c2 is just taken as f dash double dash of r by f dash of r. Now you have to consider this particular xk plus 1. We have already found out the values of a0, a1 and a2. However, we have to now substitute the values of xk plus 1 and xk. That is what I've written as r plus epsilon k plus 1 and r plus epsilon k. R gets cancelled on both the sides and it leaves you with epsilon k plus 1 to be equal to this particular term. Just simplify further, you reach this step. Multiplication, division is the inverse of multiplication, so that's why you have obtained that particular step. Epsilon k plus 1 equals to that term, so that's what you get about it. Epsilon k plus 1 equals to epsilon k minus f double dash of r into that. When you bring it on top, it becomes an expansion of binomial series as I have shown, and thus you get this term. Just find out the LCM and put it there. After doing that, you'll be getting out the term. Take 4 common outside and you'll have now obtained the value of epsilon k plus 1. So basically we just need to find out the value of epsilon k plus 1. Now for this epsilon k plus 1, the array equation associated with the Muller equation is given as what I've written down below. Sum a and p, you consider epsilon k plus 1 to be equal to a into epsilon k to the power of p. And for some a and p, you consider epsilon k plus 1, which I have written as below, which implies the value of epsilon k. You also assume a value epsilon k minus 1 given as such. When you replace it with k minus 1 with k minus 2, the RHS becomes k minus 1 because the term becomes much more less. Now you apply power 1 by p on both sides. For the particular equation, you get the following. Simplify it. Further on, you get this following step. Now you have to put these values epsilon k minus 1, epsilon k minus 2 and epsilon k plus 1 in C. By doing so, you get this following as what I've shown, and you just carefully simplify all of this. First you take all the a terms together, product of a terms together, epsilon product of epsilon k terms together, and the constant terms, and you add the power. The powers are added over there, and you have to now equate the like terms. That is, you can equate epsilon k terms powers only. That's what you need to do. So by doing that, you obtain this. Just take the LCM. You obtain a equation with the highest power cube, that is f of p equals to this function. Now to find out the rate of convergence for this method, we consider Newton-Raphson's method. Just extend Newton-Raphson's method. Substitute Pn and the differential value of it in the denominator. You get the following. I've just simplified it. Further simplifying, you get Pn plus 1 to be equal to this value. As usual in Newton-Raphson's method, first we start by putting the n value 0. So obviously p0 value gives you the 2 because you have substituted it, and in the first iteration you get the value as 1.85714. In the second iteration, when you put n equals to 1, you get the value of p2 to be 1.8395. Keep carrying on iterations in this way. I've done the third iteration, p3. p3 gives you 1.8392, and we observe that for p2 and p3 the same values are occurring after this. So therefore p 1.839 can be rounded off to p, which equals to 1.84, which is basically the rate of convergence for the Muller's method. It's simple if you follow it step by step, hence the Muller's method.